Hello, welcome to the probability class. The last session was somewhat descriptive. We started with a non-mathematical discussion on chances, and then we gradually moved towards formal definition of random experiment, sample space, then events, what is meant by occurrence of events, and then we talked about basic set theory, because sets are very essential to discuss probability. As we have already seen, that events are nothing but subsets of the sample space. There we discussed basic laws of set theory like intersection, union, complement, what's the associative rule, distributive rule, and De Morgan's rule. After having done so, we also talked about a principle called inclusion-exclusion principle, which is primarily a counting principle, and it's very useful to deal with probability. We talked about inclusion-exclusion principle when there are two sets and also when there are three sets. In fact, it can be done for any number of sets. Say, for example, n number of sets. Of course, the formula will look a little more complicated, but then it can still be done. At the end of the session, I asked you to do the same thing for 4 sets and blotted out a few confusing things while ending the session. So let me complete that part, say what is the exact form when there are 4 sets, and then I'll get into the next part, that is defining probability and what is classical probability, etc. So let me bring out the PPT first. Yeah. So here we have got 4 sets, A, B, C, and D. Inclusion-exclusion principle helps us find out the size of the union, right? So it will help us to find out the size of this union set, A union, B union, C union, D, and that will be equal to size of A plus size of B minus size of AB. I'll have to take all the 2 symbol things now. AB, AC, AD. I'm doing it systematically. Minus BC, minus BD, minus CD. By the way, what is AB? AB means A intersection B. And how many of these will be there? There will be 4C2, that is 6. See, there are 6 such things altogether, and the sign of each of them is negative. I also told you earlier that signs go alternately. First level, all the signs here will be plus, and then the next level, that is AB, AC, etc., sign will be negative. And again, the next level, the signs will be positive. How many next level terms are there? There will be 4C3 equal to 4 such terms. Let's write down all those things. ABC, that is without the D. Then if I discard C, I get this. If I discard B, I get this, and then plus B, C, D. And how many 4-letter term will be there? There will be only one, and the sign will be negative. A, B, C, D. That's the exact form here. That is the formula. All right. Now, let us move on to the session that we are supposed to cover today. Let me clear this drawing. Okay. Classical probability, that's what it is called. Say the way we'll do probability to start with, that's called classical probability. And gradually the definition will come. We are moving into the formal description of probability. And in order to do that, there's a terminology called equally likely. Outcomes of a random experiment are called equally likely if each outcome has same chance of occurrence as others. Say, if there are 5 outcomes of a random experiment, I'll call them equally likely if each one of them has got same chances of occurrence as the other 4. Now, observe a little problematic thing in this definition. Here, while describing things about chance, we are again using the word chance that is some kind of ambiguity, isn't it? So, in other words, in order to define equally likely, we are using the term same chance of occurrence. That's not quite satisfactory. However, we cannot bypass this kind of ambiguity. So let's see what actually it means, although we cannot really completely mathematically define this term. Intuitively, it will be fairly clear. So let's get into that. Okay. Let's consider a symmetric die. What it means is each side, see, a die has got 6 sides. So a symmetric die in terms of shape, size, density, etc., each side is same as any other side. Then it's quite agreeable that each of the 6 sides will be equally likely, isn't it? Although, say, you may say that it's a little ambiguous term, but even without getting into that thing, it's intuitively quite clear that each side of such a symmetric die will be equally likely to occur. And that's where the intuitive appeal comes here. Now, if you consider a typical coin, it has got 2 sides, head and tail. Now, typical coin, see, both sides have got similar kind of density and say similar kind of shape, etc. So, if we toss the coin, each side is equally likely to occur or turn up as we toss the coin. Such coins are called fair coins. And the earlier described symmetric die, where each side is equally likely, that's called a fair die. Another example. You must have seen a deck of cards. It has got 52 cards and there are 4 suits. What are those? Club, spade, heart, and diamond. And each of the 4 suits has got 13 cards, and those cards are of what type? They have got denomination, say 2 to 10, so 9 cards, 1 ace, 1 jack, 1 queen, and 1 king. So each suit looks similar to any other suit, and it has got 13 cards like that. So altogether there are 13 into 4 equal to 52 cards in a deck. Now, the deck of cards may be kept arranged in some order. Say, for example, in the order that first you keep ace, then 2, 3, 4 up to 10, then jack, king, and queen. And then you first put the club, then spade, then heart, and diamond in some order. According to your convention, you may order the thing. And if you keep the deck ordered according to your convention, and then blindly pick up a card from there, then although you are trying to do it randomly, not every card will be equally likely to occur. Say, why I am saying that? Because, say, there might be certain bias while drawing the card. Maybe you have a little bias towards the upward part of the deck. You are, although you are blindly picking up the card, you are a little biased towards the upward part. Or maybe you consciously you are trying to draw from the bottom part. In that case, you are more biased towards the bottom part. In that case, not each card of that 52 sides deck is equally likely to occur, right? I hope it is clear now. Now, let's consider another case. Suppose I shuffle the card well blindly, take the card and keep on shuffling, and then after having shuffled it well enough, then keep the deck of cards. So I don't know which card occurs where, and then I blindly pick up a card. Now, no matter whether I have a upward bias or downward bias, or I do it completely randomly, it's quite agreeable that each card will occur with same chance or has got equal chance of occurrence. So in this case, we can say that each card is equally likely to occur. However, when the deck is ordered, we could not have said the same thing. Now, we have already talked about paired die, where each side is equally likely to occur. Now, let's take a pair of paired dice. A pair of paired dice. Then, if we roll them together, we have already seen in the earlier session what's the sample space here. The sample space has got 36 sample points in this case, which gives all the combinations of possibilities like 1, 1, 1, 2, 3, 4, 5, 6, etc. Now, because both the dice are fair, here each of the 36 sample points is equally likely. Let's take another example. Suppose we have got an urn or a kind of bucket where there are 6 balls. The balls are numbered 1, 2, 3, 4, 5, and 6. The balls are otherwise similar in shape, size, weight, etc. So just by feel, you cannot distinguish them. However, 4 of them are colored red and 2 of them are colored white. Now imagine that you are blindly picking up one of the balls from the urn, and then you observe the color of the ball. Now this is the random experiment. Now the random experiment, we can write down the outcome. That will give us the sample space. Now here, you may write down the outcome this way also, that as the color of the ball that is drawn. In that case, the sample space becomes red and white. Oh, there is a little typo here. In one place, I have used red and white, and below I am using red and blue. So let's assume that there are 4 red and 2 white, and do this correction yourself, red and white. So the sample space here will be red and white because there are 4 red balls and 2 white balls. So the sample space here will be, because we are just observing the color, we can say that, okay, say in this case, the sample space will be just red and white. Now, what do you think? Are both the outcomes red and white equally likely? No, because there are more red balls than white balls. So intuitively, it is quite clear that there will be higher chance of drawing a red ball than drawing a white ball. So these two outcomes here, red and white, are not equally likely. Correct? Now, I told you that the balls are also numbered 1, 2, 3, 4, 5, and 6. So one way to write down the sample space is just write down the number of the ball that is picked up. In that case, the sample space will be the set 1, 2, 3, 4, 5, and 6. Now, look, if we write the sample space this way as the set 1 to 6 containing 6 elements, then we don't have any problem agreeing that each of the sample point is equally likely here, because the balls, other than the color, are all similar. They have got same weight and shape. So if I blindly pick up one from the urn, closing my eyes, if I pick up one, then I'm equally likely to pick up any of those 6 balls. So that's why each of those numbers is equally likely to occur. So as you see, that it may depend on how we write the sample space to determine whether each sample point is equally likely or not. Now let's get into the classical definition of probability. So here comes a little bit of mathematics. Not much, but just a basic division thing. Okay. So let's consider a random experiment with finite sample space omega. Okay. So we have a random experiment here, and the sample space omega is finite. While talking about random experiment and sample space, we have seen a few examples where the sample space may also be infinite, in the sense that it might have infinitely many elements. Say, for example, while studying the lifespan of an equipment, we had seen that it can be anything from 0 onwards, any number actually. And such sample spaces have infinitely many elements. Now, here we are considering a random experiment whose number of possible outcomes is finite. In other words, the sample space is finite. Suppose each of the outcome is equally likely. And by this time, we have got a fairly good idea by what is meant by equally likely. Let's consider any event A, that means a subset of the set omega. Okay, let me take the pen here, that will be useful to communicate. Okay, so this omega is our sample space, and this A is the event. A is a subset of omega. Don't mind, I couldn't write it properly. Okay, all right. So A is a subset of omega. How do we define the probability of the event A? It's defined as this quotient. Ratio of A, size of A, by size of omega. You remember what is size of A? That is the number of elements in the set A. And what is size of omega? That's the number of elements in the set omega. So it's the ratio of the number of elements in the event and the sample space. We use the notation P of A to denote this. So P of A equal to this, size of A by size of omega. This is the definition. So probability of A is defined as size of A by size of omega. Let's clear this and move on to the next screen. Let's take an example. Say, let's take again the die throw example. Now, if we throw a die, we know the sample space is this 1 to 6. Let's consider 3 events A, B, and C. And then we compute the probability of each one of them. How much is probability of A? That size of A by size of omega. Size of A is 3 because there are 3 elements, 1, 3, and 5. And size of omega is 6, as can be seen here. So 3 by 6, that is equal to half. We get this answer. Similarly, probability of B is equal to size of B by size of omega, 2 by 6, because there are 2 elements in B. And we get 1 upon 3. Similarly, size of C by size of omega, that's probability of C. And this turns out to be equal to 1 by 6. Let's move on. Another example, we toss a fair coin thrice. Now, if we do so, our sample space will be like this. It contains 8 elements: head, 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 tail, head, tail, head, 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 tail, head, head, tail, tail, etc. It has got altogether 8 elements. Let us consider the event A, which is there are more heads than tails. This is the event. The event says there are more heads than tails. We know that any event is either a description or the exact subset. That's how an event can be designated. Here we are describing the event as there are more heads than tails. Let's see what's the corresponding subset. Let's examine each outcome of the sample space. This is the sample space. Let's examine each outcome and see whether they satisfy the condition mentioned as A. Let's take HHH. Are there more heads here than tails? How many heads are there in this outcome? There are 3 heads because all 3 are heads. How many tails are there here? 0. So number of heads 3 is more than number of tails 0. That's why this is part of A. So answer is yes. Head, head, tail. There are 2 heads and 1 tail. So again the answer is yes. So is HTH, 2 heads and 1 tail. So answer is yes. How about HTT? 1 head and 2 tails. So the answer is no. So this is no. THH, again it's yes. 2 heads and 1 tail. This is no. This is no. And of course this is no because this has got 3 tails and 1 no head. That's why it is not part of A. So our A becomes this subset. HHH, HHT, HTH, and THH. We just took all the tick marked outcomes. So HHH, HHT, HTH, and THH. So this is our event A. Once we find out what is A, finding probability of A is very easy. That is nothing but size of A by size of omega. So 4 by 8. We have already seen that omega has got 8 elements. So 4 by 8 equal to half. Here we did it systematically for the benefit of your understanding. how to find out the exact set A. However, in many examples, we won't do it so elaborately, and it will be left to you to check which all outcomes are part of A. This is the way to check. You go through each outcome one by one and check whether they are part of A or not. In other words, whether each one of them satisfies the condition the condition mentioned in A. Let me clear this and move on to the next screen. Let's take another example. Suppose we have 2 dice are thrown. Here it is not mentioned. I should have mentioned 2 fair dice. Because when you mention fair, there is no more doubt. You know that each one of them has got 6 sides equally likely. So 2 fair dice. If 2 fair dice are thrown, what's the probability that their sum is greater than or equal to 9? So here, sample space is equal to this. We have seen it multiple times by this time. And how many elements are there in the sample space? Sample space size is equal to 6 into 6. That is equal to 36. Now, what is A? A, the event A is, we are trying to find out what is the probability that their sum is greater than or equal to 9. That's what we intend to do. What's the probability that their sum is greater than or equal to 9? Right? So let's designate that condition in an event. So let's designate the event A to be this event, when the sum is greater than or equal to 9. So what is the concerned event A here? That contains all pairs of outcomes, that is ij, where I plus j is greater than or equal to 9. Right? So if I say 1, 1, is it part of A? No, because their sum is equal to 2, which is not greater than or equal to 9. So 1, 1 does not belong to A. So let's systematically see which all outcomes belong to A. By systematically, I mean, first let us fix the first element and see which all are the possible second die outcome, and that way. So if the first die gives 1, is it possible to have summation greater than or equal to 9? Answer is no, because when the first one is 1, no matter what the second one is, the summation can be at most 7. So it cannot be greater than or equal to 9. So nothing starting with 1 can be part of A. By the same logic, the outcome cannot have the first element 2 in order to have the summation greater than or equal to 9. So the first possibility is the first element can be 3. And in that case, what should be the second element? Can it be 1, 2, 3, 4, 5? No. It can only be 6. That's why 3, 6 comes here. Okay? Next, we move on to 4. If the first element is 4, let's examine which can be the second element. When the first element is 4, the second element cannot be 1, 2, 3, or 4. In that case, summation will be less than 9. So it can be either 5 or it can be 6. That's why we have got 4, 5 and 4, 6. Similarly, when you take 5, when you take the first element as 5, then the second element can either be 4 or 5 or 6. So that's why we are getting 5, 4, 5, 5, 5, 6. And when the first element is 6, In that case, we can get 6, 3, 6, 4, 6, 5, and 6, 6. So altogether, how many elements are there in A? How many elements altogether there are? Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So size of A equal to 10. Once we find out the size of A, size of omega is already known. So probability of A now can we find out as the ratio of these two? 10 by 36, that is 5 by 18. Right? Okay. I will do one thing here. Let me clear this drawing. And I will give you one nice way of writing the outcome in this kind of problems that will help you in solving other problems. See, here we are throwing 2 dice. So we can write down the outcome this way. Drawing is getting horrible, but I hope you understand. Once I write it down properly, you should be able to understand. So 1, 2, 3, 4, 5, and 6. This side also 1, 2, 3, 4, 5, and 6. Suppose we write down the first, the die number 1 outcome, we write on this side. And on this side, we are writing the outcome of die number 2. So what does this cell indicate? This cell indicates the outcome 2, 3. That means the first die is 2, and the second die is 3. Now, after having written this way, let's get back to this event A. Which all outcomes satisfy this? 3, 6. So 3, 6 means this one, right? Now comes 4, 5, and 4, 6. So 4, 5, and 4, 6. Then 5, 4, 5, 5, 4, 5, 5, and 5, 6. And then 6, 3, 6, 4, 6, 5, and 6, 6. Now, although the drawing is very ugly, still you can see the pattern here. And it's easier to work out the problem if you draw a simple diagram like this. Then you can easily find out what is the size of A, and all the elements of A are appearing in this part, right? Appearing in this part, some triangular, in some triangular area, and how many elements are there is also easy to see. 1 plus 2 plus 3 plus 4. So altogether there are 10 such elements that we have already seen without drawing this diagram. And this way, perhaps you will agree that if we draw the diagram this way, it gets a lot clearer. For other problems, more complicated problems, definitely it will be very helpful. So keep this thing in mind. Now let me clear this drawing. Okay. Now let me move on to the next screen. All right. So this gives the properties of probability. Probability defined the way we have done gives us certain properties. And what are those? Those are numbered here 1, 2, 3, 4, 5, and 6. These are basic properties, and there will be some more properties. But to start with, this should be good enough. Let me take this one first. 0 is less than or equal to, by the way, here A, B, C, all these will denote some events, and omega is the sample space. Okay. So the picture is like this. This is omega and this is A. Now let's look into this property. We know that size of A is a non-negative number because size can never be negative. So 0 is less than or equal to size of A. And also, because A is a subset of omega, we can write size of A is less than or equal to size of omega. Now, this gives us that if we divide all these sides by size of omega, then we'll get 0 is less than or equal to size of A by size of omega is less than or equal to 1. And in turn, this gives us 0 is less than or equal to probability of A, because this ratio is nothing but probability of A, and that is less than or equal to 1. So you see how easily we get this property. This is a very interesting property. It tells us that probability scale is always between 0 and 1. Like Celsius scale always measures temperature between 0 and 100. Fahrenheit scale measures temperature between 32 and 212, right? If I remember it correctly. However, one difference between temperature and probability is we all agree that temperature can go beyond this scale. Say, this is the scale to measure different temperatures for water, starting from ice cold up to boiling water. However, temperature can be higher than this or lower than freezing point. However, when you come to probability, this scale is always between 0 and 1. It can never be negative or never be more than 1. So while solving some problem, if you get an answer, some negative number or say 1.5, you know definitely your answer is incorrect. Let's clear a little bit of this. Okay, now probability of omega equal to 1. Why is it so? Because probability of omega is nothing but this ratio, that is equal to 1. And how much is probability of the impossible event or null set? That is nothing but ratio of size of null set divided by size of omega, that is equal to 0. That's why we get this property. Suppose we have got two events. Okay. The events are namely A and B. And event A is part of event B. Either same or event B is larger. That is the symbol, this. That means A is either a smaller event than B or they are equal. In that case, what happens? If that is the case, A contained in B, this gives us that size of A is less than or equal to size of B. Now, if we divide both sides by size of omega, then we get size of A by size of omega is less than or equal to size of B by size of omega. And these are nothing but probabilities. So PA is less than or equal to PB. Clear? All right. Okay. We have this drawing. Now, how about this? See, omega is nothing but A union A complement. Right? Like this. This is omega. This is A, and outside is A complement. This part is A complement. So A union A complement is equal to omega. Not only that, if you add the number of elements, then number of elements in A plus number of elements in A complement will be same as the total number of elements. Okay? Intuitively, it's very clear. Or you can apply the inclusion-exclusion principle. Say, what is it? Size of omega equal to, this is equal to, by inclusion-exclusion principle, A complement minus of A intersection A complement. Is there any element in A intersection A complement? No, that's null set, because no element can belong to both A and A complement. That's why this is being a null set, this is 0. That's why we get size of omega is nothing but size of A union A complement, and that is equal to size of A plus size of A complement. However, it's intuitively quite clear why this should hold, and you don't need to apply the complicated, not actually complicated, the more elaborate inclusion-exclusion principle for this. This is quite obvious. Okay. Now, we have size of omega equal to size of A plus size of A complement. If we divide both sides by size of omega, we get 1 equal to P of A, because this size of A divided by size of omega is nothing but P of A, and this one becomes probability of A complement, because this is nothing but size of A complement by size of omega. Then, I hope this is clear. All I'm doing here is, let me write it down more clearly. Okay. I'm dividing by omega, size of omega. So left hand side I get 1, right hand side I get this divided by this plus, my writing is going out of control, so please bear with it. And this becomes 1 equal to P of A plus P of A complement, and this in turn implies, yeah, this is better writing, right, compared to this. So this gives us P of A complement equal to 1 minus PA, and that's what this one is. Now comes inclusion-exclusion principle. Before that, let me clear this. Okay. Now, let's talk about this. Why is it so? By simple application of the inclusion-exclusion principle for sets, what is that? We know that A union B, size of that is nothing but size of A plus size of B minus size of AB, or A intersection B. Dividing by size of omega, on both sides we get size of A union B divided by size of omega equal to size of A by size of omega plus size of B by size of omega minus size of AB by size of omega. And now writing in the notation of probability, we get left hand side is nothing but probability of A union B, and then right hand side becomes PA plus PB minus P of AB. And that's how you get this formula, right? Now, sorry, why is this coming? Okay, clear this. This has come up. I don't know how to handle this. Just bear with me, please, for a few minutes. Yeah, hopefully it is taken care of. Sorry for the disturbance. Somehow it came up over the screen and I had to remove that thing. I had no clue how to handle that. So hope this is undisturbed, the rest of it. Okay, let me pick up drawing once again. Can I draw? Yeah. So we have already taken care of this, except this part. Now, how about this? If the diagram is like this, suppose A and B are disjoint. In that case, A intersection B is null set. So if we put that thing in this formula, what we get is P of A union B equal to PA plus PB minus P of null set. And P of null set is 0. So that's why you get this one when the diagram is like this. In other words, when A and B are disjoint. Look at this. This is an interesting thing. And this will help your intuition also. Let me remove this diagram. Okay. Suppose you are measuring some area. Suppose this is area A and this is area B and they are non-overlapping. So somehow if you can find out area of A and area of B, knowing that they are not overlapping, you can just add them to find out what is the combined area of A and B. However, if they are overlapping like this and this, you cannot say so. And same thing for volumes in say 3D space. If there are two enclosures which are non-overlapping, then in order to find out the total volume, you can simply add them. And that's what is happening here. So if A and B are two disjoint events, then their probability simply add up like adding areas of non-overlapping areas or for volumes of non-overlapping 3D regions. So this is helpful intuitively. And not only for two events, if there are three or more events which are mutually exclusive, we'll define that term later. If they're non-overlapping with each other, you know intuitively what it means. In that case also, probability of the union of all these things will just add up, will be summation of the individual probabilities. We'll get into that thing later. Now, let's talk about this. Again, this will be simple application of inclusion-exclusion principle. Say Let me go to the other board. That way it will be easier. Well, now we are here. So this gives me more space. I'm just writing down the inclusion exclusion principle of set theory. Now let's divide by size of omega. By this time you have seen that it's the standard trick. So if we divide by size of omega, the left hand side becomes probability of A union B union C. I'm not writing down again that step in details. You know what I mean. I'm simply dividing both sides by size of omega. So this one will give me this term, and then I will get PA. This will give this term plus P of B. See? This is the inclusion exclusion principle of probability when there are three sets. And similarly, you can write down the inclusion exclusion probability of probability, inclusion exclusion principle of probability when there are 4 sets or 5 sets, etc. And what I was talking about, if A, B, and C are not overlapping with each other, if the diagram is like this, here is A, here is B, here is C. In that case, each of these terms, AB, BC, CA, ABC, all these things, all these probabilities turn out to be 0, and you will be left with only this part. Again, you see the similarity? As they are non-overlapping, their probabilities are adding up like non-overlapping areas. Let me go to the PPT once again. All right, let's illustrate with the help of one example how you can use this rule to compute some other things. Say you are given probability of A, probability of B, and probability of A intersection B. Okay, so here is a small diagram. Small diagram here. This is omega. Here is A. Here is B. This is A intersection B. Probability of these three things are given. PA is equal to half. PB is equal to 3 by 5. Intersection probability is 1 by 3. Then how do you find out the following things? This, or this. Let's see one by one. That way, the rules will be revisited and you will get a better grip on those rules. Because those rules often help you to find out the probabilities. Probability of A union B is nothing but this. This is the inclusion exclusion principle. And by putting these figures, half plus 3 by 5 minus 1 by 3, if you do this calculation, the denominator LCM is 30, and then here I will get 15. 15 plus 6, 21. Here I will get 15. Here I will get 18. So 33 minus 10. So 23. 23 by 30. How much will be this? How much will be this? Probability of A intersection union B intersection. by application of De Morgan's rule, we can write it as probability of A union B whole complement. That's what is De Morgan's rule. And then by applying rules of probability, remember the rule, probability of A complement equal to 1 minus probability of A. We are applying that. Then this one can be written as 1 minus probability of A union B, like this. And A union B we have already found out to be 23 by 30. So 1 minus 23 by 30, that is 7 by 30. How about this? That is again by De Morgan's rule, probability of A intersection B whole complement. That is again 1 minus probability of A intersection B, and A intersection B is given to be 1 by 3. This one. So 1 minus 1 by 3 is equal to 2 by 3. Also, how do you find probability of A B complement? What is AB complement? AB complement means all those events which satisfy A but not B. That's what is AB complement. In other words, A has occurred but not B. This is the precise event meant by AB complement. So how do you find out the probability of that? See, let me clear this thing first. We need to find out AB complement, right? So here is A and here is B. This is A, this is B, right? Now, A can be written as AB union AB complement. Why is it so? Let's analyze this. Sometimes you intuitively feel some set identity. Okay. And in order to establish that identity, what you are feeling intuitively to be correct, you need to show two things. First of all, any element on the left-hand side should also belong to the right-hand side, and any element on the right-hand side also should belong to the left-hand side. Say, in that case, what happens? Both the sets must be subsets of each other. That means both the sets must be equal to each other. That's the standard trick. So let me repeat. If I need to, keeping this problem apart, if I need to show any two sets X and Y to be equal, first I show that X is either contained or equal to Y by showing that if I take any element here, then that element also belongs here. And then we show that Y is contained in X by taking any element here and showing that to be part of X. Once we establish both these inequalities or both these containments, not inequalities actually, containments, then it follows automatically that X, set X is same as set Y. Let's come back to this particular thing. Is that what's happening here? Let's take any element. Let me erase this part. That way it will be less confusing for you. Okay. If I take anything on the right hand side, take any element. Typically, outcomes are denoted by omega. Okay. You may write it, you may use any other letter, but typically we use omega. Take any outcome omega, which is part of the right hand side. Now, part of the right hand side means either it belongs here or here. If it belongs here, then of course it must belong to A, because in that case omega belongs to both A and B. So in that case omega belongs to A. Now, if omega belongs to this part, then also omega must belong to A, because this part is nothing but A intersection B complement. So either way, we have argued that if omega belongs to the right hand side, then it must belong to A. In other words, this one, see, any omega here, any omega on this side must belong to A, right? So we have established that that A, we have established that right hand side is contained in left hand side. Why is it so? Let me overall go through the argument once again. We have picked up any element on the right hand side and shown that thing to be part of the left hand side. So that's why right hand side has been shown to be part of or contained in left hand side. Now let me take any element on the left hand side. Suppose omega belongs to A. In that case, two scenarios are possible. Omega may either belong to B or may not belong to B. If omega belongs to B, in that case, omega belongs to AB, right? So two scenarios are either omega belongs to B. One scenario is we have taken omega belonging to A, right? Two scenarios are possible. First scenario, omega belongs to B. In this case, what happens? Omega already belongs to A and it also belongs to B. So omega belongs to AB. In the other case, suppose omega does not belong to B. In that case, omega belongs to A, B complement. So either way, it belongs to the right hand side, right? So any element on the left hand side is an element on the of the right hand side. That's why left hand side is also contained in right hand side, and so they must be equal, right? They must be equal. If this got a little complicated, don't worry. Don't forget about the details of these things. It's not that necessary. Just remember this rule. This will be helpful. Let me clear this drawing. So what we wrote here, A is nothing but AB union AB complement, and observe that they are not mutually exclusive. They are disjoint. AB is disjoint from AB complement. Why is it so? Because AB, any element in AB must also belong to B. So it cannot belong to B complement. That is, it cannot belong to AB complement. So they are disjoint. So probability of, that's why after being convinced on this thing and observing that these two events are disjoint, we can write that P of A equal to P of AB plus P of AB complement. Then that gives us P of AB complement is nothing but P of A minus P of AB. And we already know that thing. How much is P of A? That is half. And how much is P of AB? This is 1/3. So that's why we get this to be 1/6. So that's what is noted here. I just explained the note and that took a little time. If you are just too confused about that thing, don't bother. Just remember this rule and apply this rule to find out such thing. Getting a little grip over basic set theory helps you to solve complicated probability problems. Let me clear the drawing and move on to the next screen. Yeah. empirical probability. What is the empirical probability? This is also known frequency probability. Frequency probability or empirical probability. It's an experimental thing. Consider an event A for some random experiment. Like if you are throwing a die, your A may be outcome is less than 3, in which case A is equal to 1 and 2. A can be anything, and random experiment can also be anything. Now suppose you repeat the same experiment a number of times, actually a large number of times. Because what happens when you repeat the experiment a large number of times, then it makes more sense to take ratio, etc. We'll see that thing later. So for the time being, just imagine that you are repeating the experiment capital N number of times. Now, each time you perform the experiment, you can also observe whether the event A has occurred or not, right? Because once you perform the experiment, you know the exact outcome. So you know whether the event A has occurred or not. So as you perform the experiment, each time you keep on writing whether the event has occurred or not. So each of the capital N trials that you take, you keep on writing whether the event A has occurred or not. And at the end of capital N trials, you find out how many times the event A occurred. Call it small n, the number of times the event A occurred. Now, the empirical probability of the event A is defined by the ratio small n by capital N. In other words, ratio of the number of occurrence of the event and the total number of experiments performed. So that ratio gives the empirical probability of the event A. This gives an experimental way of determining probability. Let's take an example. Consider the die roll example once again. And suppose the outcome, suppose the event A is, the outcome is odd. In writing in terms of subset, what is A? It consists of 3 elements, 1, 3, and 5. And after having rolled the die 10 times, suppose our outcomes are, let me take the pen here. Suppose the outcomes are 4, 3, 5, 3, 6, 2, 4, 1, 5, and 3. These are the 10 outcomes that we observed while rolling the die 10 times. Of course, if you roll the die 10 times again, outcomes will be something else. That's quite understandable. So suppose this is the outcome I got. In this case, what is my capital N? Total number of trials equal to 10. And what's my small n? The total number of occurrence of event A, in other words, frequency of event A, that is equal to 6. Because let's observe which all outcomes satisfy A. First outcome was 4. A was not satisfied. Next outcome was 3, and it's an odd number. So A has occurred. Next time the outcome is 5. So A has occurred. Next outcome 3, A has occurred. 6, no. 2, no. 4, no. 1, yes. 5, yes. 3, yes. So the event A has occurred 6 times. That's why my small n here, or the frequency of occurrence of A is 6. So empirical probability of the event A is n by n is equal to small n by capital N is equal to 6 by 10 equal to 3 by 5. See, it depends on the experiment, right? Next time, if you perform another 10 rolls of the same die, the answer will be something else. Now comes empirical versus classical. The same event, by definition of classical probability, we have already calculated the probability of that event to be equal to half, because number of favorable outcomes or the size of A is 3 and size of omega, the sample space here, is 6. Ratio of these two numbers is equal to half. So by classical definition of probability, the event A has got probability half. However, empirically, when we do experiment and try to compute probability of the same event, we got the answer to be as we calculated last time, that is 6 by 10 equal to 3 by 5. So it's different from 3 by 5. Classical probability is some kind of ideal value, right? And it gives a theoretical value. In order to calculate that, you don't need to perform any experimentation. However, empirical probability is always experiment-based. You perform the experiment or the random experiment a number of times, find out how many times the event occurred, take ratios, and then find out the empirical value of the probability. If we perform a fairly large number of trials, say a few hundred times or few thousand times, in that case, empirical value is expected to be very close to the theoretical value, or say empirical value let me repeat that thing once again. If we perform the random experiment a large number of times, in that case, empirical probability that you find will be very close to the classical probability value for the same event. However, if you happen to get a very different value, then you actually doubt the assumption of equal likeliness, that maybe all the outcomes are not equally likely. Because you remember, while calculating probability by the formula size of A by size of omega, we used a crucial assumption that each outcome is equally likely. And based on that assumption, our probability calculation is based. So when your empirical value is very different from the classical probability value that you calculate, in that case, there is sufficient ground to question that assumption that each outcome is equally likely. All right. So that brings us to the end of this. Okay. Thank you very much for listening. Hope you understood this, and see you in the next class.